Hi guys, so this is where we left off. Here we're talking about it says if we know a capacitor's voltage, okay, so here's the capacitor. Its voltage is delta V, and the distance between the plates is D. So that's actually a good point. When I just drew this delta V, and it looks like it was like a distance. That's something that people do, is showing you that the difference in potential between those two spots is delta V. Now, if you really are being careful about it, one of those spots is higher than the other, so delta V could be positive or negative, but generally if you're going to write something like that, you're talking about the absolute value of it. So this is just a typical capacitor, and because we're just talking about the absolute value of that delta V, it doesn't matter which one of those plates is positive or which one's negative. But, if that's positive and that's negative, then here, let's change up the color. There's my electric field, always going from positive to negative, and the value of that electric field is delta V, or here they cited that V with a sub C capacitor, divided by that distance. Okay, so that's useful. That's uniform. Please don't use this equation for anything that's not uniform. So look at the units. It's a volt is a potential difference per meter. So electric field, which we'd been saying, right? Electric field was force over Q, so that's Newton per Coulomb, is equal to a volt per meter. So that's kind of fun. And remember, the volt was, right, that was potential energy per charge, so it was a joule per coulomb. Right, by the way, these are things like this. So it's a joule per coulomb, right? That's a Newton meter per coulomb. So there you see volt. You could write lots of things. Oh my gosh, a Newton meter, which is a joule, is also a volt times a coulomb. These kinds of things, there's a gazillion different ways of playing with the units in this semester. Okay, so when we originally looked at like potential energy curves, we talked about F equals negative du dx, right, being the negative of the slope of the u versus x curve is the force, right? Or we also talked about this word gradient. It's the gradient of the potential energy. And equilibrium is where F equals 0, so the slope is 0. So if you will see this in this context in a couple different ways. You could have this as if you actually have a u versus x graph, you can do the same thing and get the electric field from the force, right? So if that is, right, an F equals 0 situation, that also means that E equals 0 right there, right? Or if you actually have a V versus X, then the slope is equal to just the negative slope is equal to the electric field, right? By the way, I also sort of expanded on this gradient thing. This is a del. These weird looking delta-like things are partial derivatives. What a partial derivative is if you have a function of x and y, partial f, partial x is you take a derivative of this and you just treat y as a constant. Okay? And so that's what this gradient is, and then you can see it's a vector, right? There's an I hat, j hat, k hat situation. But in general, when we write something like this, we're just looking for the x component. So that's what this is, right? It's just the x component of the electric field is just that dV dx. And don't forget that negative. Okay, so when you put a point charge Q down, it creates an electric field, and that also creates a potential. So to explore that, we to get at potential, we like to look at potential energy, right? So if I put, we do this WWPCF, right? Is what would a positive charge feel, right? What does it want to do, right? If I put this little positive test charge near this Q, and it's a distance r away, it feels that electric field from the Q, right? And it makes it want to go far away, right? It experiences a force away from it, and so it's going to accelerate away. So we know that it has a high potential energy when it's close, right? And it's a positive charge, so a high potential energy means it's a high potential, right? And as you can probably imagine, the further away you get, the lower your potential gets, right? Due to the point charge Q. So this in the blue box, my gosh, I'm really into these blue boxes today. So V equals 0 at R goes to infinity. Remember when we did gravity, that potential energy was 0 at R's infinity, and it was because it was like a 1 over R thing. It's going to be exactly the same thing here. But this is for the potential created by a point charge, okay? So let's actually calculate the potential, okay? So we're going to start with this equation. So that's really just that basic relationship between potential and electric field. We're going to start it at this point. So the initial is at R away, right, from the Q. And the final will be when it gets infinitely far away. Okay, so this is delta V is equal to negative integral from the initial to the final point, E dot dl. And again, dl, you can think about it dx, dr, but that's just sort of a traditional way of writing it. So our final point is infinity, and our initial point is at R. So this line is just plugging those things in. So initial and infinity, here's my initial, here's infinity. And what's my electric field due to a point charge? My electric field due to a point charge is KQ over R squared, all right? And so it's clear that we're working in R, so we're going to change that dl to a dr. And as you can see up here, my dot product gives us just a 1. All right. So now we're just going to keep going. So my left-hand side, I'm just going to leave that V infinity minus VR. And then I have a negative integral from R to infinity. I'm just rewriting KQ over R squared as KQ R to the negative 2, just to help me with my calculus. Because the integral of R to the negative 2 is going to be negative R to the negative 1. Okay, remember that negative is that one. Okay, so again, it's like fun with negatives. And so this, of course, is evaluated. The initial point is R, final point is infinity. So it's evaluating at the final minus evaluating at the initial. So now we have this side and this side. So 0 is where we've defined our V equals 0 at R's infinity. So that's why this first term is 0 minus V sub R equals, and then on this right-hand side, something over infinity is 0, which this is why, right? This is why we have this definition. And so here we are. The potential created by a point charge is KQ over R. And again, it's a scalar and it has a sign. So if Q is positive, then V is positive, right? If it's negative, it's negative. Or if the Q is negative, then the potential that it creates is negative. And those are scalars. And so they add. like actual numbers. So what we have here, so it says a positively charged particle produces a positive electric potential. So a negatively charged particle produces a negative electric potential. So that's what I was just saying. And they add like scalars. So this first thing where it says V equals, that's the sum of all the different charges, right? So what is this picture that we have here? We have three different charges, Q1, Q2, and Q3. And I'm interested at point P, what is the potential? So remember, we've asked these kinds of questions about, we have a configuration of charges. What is the electric field at a certain point in the vicinity of those charges? So now we're just asking a similar question. We have a configuration of charges. What is the potential at a point in the vicinity of those charges? And in some sense, this is even easier because with electric field, when we had to add up the electric fields, we had to worry about vectors. But these are just scalars. So that is pretty nifty, actually. So this part is actually pretty easy. So the potential at point P is the potential that Q1 creates there, which is K Q1 over R1, plus the potential that Q2 creates there, K22 over R2, etc. Okay? So remember, if Q2 was negative, then, this would have, this would be a negative number, right? So if you're asked a question like, where in the vicinity of these charges is the potential zero, right? You are asked that kind of thing for electric field all the time, right? Well, in that case, you better hope that they're not all the same sign. If they are the same sign, there's no way to get a potential equal to zero. So that's useful. Okay, so here it says the electric potential V at a point in the electric field of a charged object is V equals negative W infinity divided by Q naught equals U over Q naught. So W infinity, it's the work that would be done by the electric field on a positive test charge Q naught where it brought from an infinite distance to this point. And U is the electric potential energy that would then be stored in the system. So this idea of you start with a charge at infinity and then you bring it in and place it where it is right now is a very, very common theme in all of this discussion. So when we're looking at these two charges, you've got Q1, Q2 right there with a distance R between them. The potential energy of this system, okay? So remember things, I hold a ball above the earth, even though we say things like, it has potential energy. Really, it's the ball earth system that has potential energy. And here, when you're looking at point charges, it's much more natural to think about that. So the potential energy of this system of Q1 and Q2 sitting there is equal to the amount of work required to assemble this if you bring the charges from infinity. It takes nothing to bring the first charge from infinity to where you are. So you just start with plop Q1 down. That took no work. Now, to bring Q2 to that place, you have to do work because it doesn't want to go there, right? So you have to bring it there and you're doing work. You're applying a force over that distance, okay? And that force is going to be varying, right? Because it's a point charge. So KQ over R squared is that electric field. And so it's going to have a varying force. So what happens when you actually get it there? You did a certain amount of work, and now that system has a certain potential energy in it. And you can look at it like this, U12, so that's the potential energy in that system of charge 1 and charge 2. You can think about it as you placed Q2 at the potential that Q1 created a distance R away. Okay, so you can write Q2, then that V1 is KQ1 over R. And so it's KQ1, Q2 over R. You can, of course, looking at that symmetry, do the same thing, put Q2 there, and then bring Q1 in. Q1 is now experiencing that potential that was created by Q2, and so you get that symmetry. These arguments should be pretty similar, as the ones where we talked about getting the force from the electric field. Okay, so very often you'll see questions that say things like, how much work did it take to place something there? And what they are asking for is the potential energy of the system. That's a very, very nice, a nice tip that I'm giving you, because this is a phrasing that's used all the time, and you're like, well, why don't you just tell me to calculate the potential energy of the system? And that's what I'm telling you to do. So like this thing on the left, you've got a square. So you've got a Q1, Q2, and Q3. Those are those red guys. And then say I want to place Q4 right there. To calculate the work that would be required to do that, I have to calculate the potential energy. So that's all the different combinations there. So U12, U13, U14, and then U23, U24, right? Because we already took care of U12 and U21. Those are the same thing. So you don't have to calculate it twice. So I have a link here in the slide deck that work to bring three charges close together. That's exactly the kind of problem I'm talking about, where you're just calculating the potential energy of the system. I think that's a Khan Academy one. And actually Khan Academy has some good discussions of potential. So if you're looking for extra resources like videos, you can check out Khan Academy. They've got some good ones. Okay, so right, this whole time we keep talking about gravity versus electrostatics. So every now and then it's nice to sort of summarize and see what we got here. So if we're looking at 2-point charges or masses that are separated from distance r, you can see the force, just, kq1, q2 over r squared, gm1, m2 over r squared. The big difference here, of course, is the directions that are possible. Gravity is only attractive, but electrostatics, you can attract or repel. The potential energy comes from taking that integral of that force right above you, right? And then a gazillion negative signs later, this is what you get. Now, remember we did a whole thing about the fact that gravitational potential energy is always negative, right? And that's because the potential energy at infinity is 0, right? And so that works, but it's always negative because it's always attractive. But because potential energy for electrostatics can be positive or negative, right? Again, if it's negative, that's because one of those charges is positive and one is negative, so they're going to attract. So just like gravity. But if they're both positive or both negative, then the product is going to give you a positive number, and the potential energy of that system will be positive. So hopefully that makes sense. If you've got two positives or two negatives that are near each other, of course that's going to have a big positive potential energy, because they're going to want to get away from each other, right? They're going to want to lower that. All right, so for fields, we get E equals Fe over Q, right? So you just get rid of one of those Q's, so it's that KQ over R squared, and then of course our gravitational field is GM over R squared, and that is a field that's created by a point charge mass a distance r away. So there we have electric potential, that's our KQ over R, and so you might sort of be asking yourself, what is gravitational potential? And the idea behind it is, of course, that it's the potential energy per mass, but maybe it's not so obvious what you should be thinking about conceptually. And so that's what I want to do right now. So to do that, let's look at the uniform situation again, right? So we've got our positive charge experiencing a high potential energy in the location of the high potential, right? So all of this that I have right here is just a repeat from one of the previous slides, okay? If you look, start looking right here, the change in potential energy is negative of the work done by the electric field, right? So negative QED. If you divide both sides, right, by Q, right? Remember, delta U is Q delta V, right? So you can get that delta V is negative ED, and you'll see that a lot. And that negative, it's there because the potential drops as you go along the electric field, right? You go from high to low, right? You follow the electric field line, your potential is going to drop. And that's super important. And I keep sort of teasing you with all this equipotential line stuff that we're going to do next time, but it will really, really help, hopefully, with this intuition. But honestly, that negative sign, I almost always ignore it and then just work it out myself, right? So you can just use delta V equals ED for the magnitude of the potential difference. But then if you're trying to figure out which one's high, which one's low, then you use your brain. So back to the question is, what is gravitational potential? So here's our ball. I'm going to drop from H to 0. And there's our U equals mgh. Well, if V is U over m, then our kind of potential is GH. But honestly, when we're thinking about uniform fields, height is really where your brain is going to go. Okay. What's nice is that we kind of did this derivation using this uniform field, but that height or elevation is going to be something that we use a lot of in our intuition. And so you can kind of see this here. So what this is there's a positive charge here and a negative charge here. It's a dipole. And so this is a way of envisioning our potentials. And so this has a really positive potential. So you see these elevations, and this is a negative potential. So there's a link, obviously, in the slide deck. This electric field and potential visualization. We're going to use this a lot next time. But this is the 3D view. And then when you press the equipotential view, it'll turn into something that looks like this. And again, these are the equipotential lines that we're going to start talking a lot about. And you can see that it kind of reminds you, hopefully, of something like a topographical map. So if you've never looked at a topographical map, please go find one and learn about them before we tackle the equipotentials next time. All right, I hope that helped.